So at the end of, all right guys, let's do this. College. Let's get started. Although I'm not nearly, I know Professor Bergdahl, if you've ever had him for either summer school or 232, he'll get visibly angry at like people looking at their cell phones and stuff, or computers. I don't, but we just had a conversation over the weekend about that, and I thought it was funny because I had Professor Bergdahl for chemistry class, and I remembered how we were just afraid of him. I know I ate lunch with him 3 days a week. So, no reason to be afraid of Professor Bergdahl. He's actually awesome. So, at the end of lecture on Friday, we were wrapping up electrical aromatic substitution. Lights. Nice. I was thinking the exact same thing. Okay, so at the end of lecture, we were talking about electrical aromatic substitution and little tricks that electrical aromatic substitution can play in us. And one of them was the fact that a nitrile, an aniline or an amine, well, it should be a really good electron donating group. It is so electron rich. What I mean is nitrogen is not very electronegative compared to oxygen, and it's got this lone pair of electrons right here. And so these are fairly high energy basic or nucleophilic electrons. And so if you try to do a typical Friedel Crafts or any kind of chemistry that we talked about under acidic conditions, what's actually going to happen is instead of doing an electrical aromatic substitution at first, the amine is going to attack the Lewis or Bronsted acid, giving us this ammonium salt. And so now it's an electron withdrawing group, so it's going to be a slower reaction that's going to go meta. And I told you guys the trick to get around this is via taking the nitrogen, using an acid chloride and some base. In this case, the base I chose was pyridine, and that will allow us to do an acetylation. In other words, bring an acyl group or a carbonyl out of the amine. So we go from an amine or an aniline to an amide. And amides, the nitrogen, the lone pair of electrons on the nitrogen, the amides is going to be more delocalized, because not only is it delocalizing through this, it's now delocalizing through the carbonyl. So it's not nearly as basic. It's still electron donating, but it's not nearly as electron donating. And since it's not as basic, it's not going to attack the AlCl3. Instead, it is going to just be an electron donating group, just like methoxy, and do an ortho-para-directed chlorination, nothing changing, giving us the major product. As in most things we've talked about, the major product is going to be ortho. But again, most of the numbers they've shown you so far with electrophilic aromatic substitution with ortho-para directors, it's been like what, 2 to 1, 3 to 1, maybe 4 to 1, favoring para with a little bit of ortho. So we're going to get a mixture, right? We're going to get mostly ortho with a significant amount of para. Nothing changes, but just for the ortho case, what's going to happen now is now we need to take out the acetyl group. And this is really chapter 17 chemistry, but just so you guys know how to do it, you take base and water, and the base will in essence attack the carbonyl. And I'm just going to gloss over the mechanism now, but we'll go over it later in the lecture. We'll eventually, base and water will clip off our acetyl group or acetate and give us our product back. So in the case of anilines, we have to do this trick where we make the amide, do the chemistry, and then take the acetyl group off using base and water. The base and water mechanism will make sense in chapter 17. There are some other things in the notes from this chapter. Read through them yourself, ask me questions. But really the only thing left in the notes is, you guys remember the sulfonylation, right? We're going to take SO3 and sulfuric acid. You guys remember that that is reversible. So let's say we wanted to get this ortho as the major product, rather than para, then all you do is your first step, you do a sulfonylation, so SO3 and sulfuric acid, and that will give us our major ortho product. There'll be some para, sulfonylated stuff, but the major stuff will be ortho. All right, so now what the sulfonyl group did effectively was it blocked our para position. So now we can do our fetal Crafts chemistry. So the AlCl3 and Cl2, and a little bit of chlorine at this position. Then we can take our sulfonyl group off. How do we take a sulfonyl group off? Sulfuric acid and reflux. The key to taking these guys off is sulfuric acid and reflux. I went over the mechanism later on. And the nice thing about sulfuric acid and reflux, those are pretty harsh conditions. So they'll actually take the acetyl group off for reasons, again, will make sense in chapter 17. But anyway, so we block this position with our sulfonyl group. That allows us to put our chlorine here. And then it's just a matter of taking this out using dilute sulfuric acid and reflux. So H2SO4 and reflux. That will take this off. And frankly, that will take this off too, but just to be safe, let's throw in our second step being our base and water. Let's use sodium hydroxide to take it off, and water. So the sulfuric acid and reflux will take this off, and then sodium hydroxide and H2O will take this off, giving us our desired now orthochlorinated aniline. So just something to think about. You can use these little chemical tricks to get around the para being the major product, or the fact that amines are so reactive they'll actually act as bases to give ammoniums that will be electron withdrawing instead of electron donating. So just for reviews, these are in the notes. What I really need to start right now is chapter 13. I said chapter 16. So chapter 16 is back to carbonyls. Chapter 16 is back to carbonyls. I think the next time I teach this class, I think I'll actually move chapter 16, 17, and 18 up to before electrical aromatic substitution. Because chapter 16 is going to get back to kind of what we were talking about in chapter 12. So nucleophilic additions into carbonyls. Chapter 16, in fact, focuses on two specific carbonyls, aldehydes and ketones. Chapter 17 focuses on carboxylic acids. And then chapter 18 gets into some it gets back to ketones, but we look at ketones from a completely different direction. But now, chapter 16 is going to seem a lot like chapter 12. And there's good reason for it. So let's remember all this aromatic stuff, but now we're going to pivot again to chapter 16, which is aldehydes and ketones. I'm not going to go over the nomenclature of aldehydes and ketones too much. I'm just going to show you some quick examples. For example, simple aldehydes. You take your base. So in this case, it's 1, 2, 3, 4, 5. So it's a 5-carbon chain, so that's pent. So it's pent, there's no double bonds, so it's pent-N. And so it ends in an aldehyde. So you know how with alcohols we end in al, like methanol or butanol? With aldehydes, we end in al. A-L, al. So this would be 1 pentanal. Al for aldehyde, pent for 5 carbons, and the 1 is coming from the fact that the aldehyde is on the end carbon, and the numbering doesn't change from 232. So the carbon with the substitution gets the lowest number. So 1 pentanal. But the big thing is aldehydes end with al, A-L. And then ketones. Ketones end in -one. So what would this ketone be called if ketones end in -one? Pentanone, exactly, 2 pentanone. That's pretty much all I do with nomenclature, right? So ketones end in -one, as in pentanone. A lot of times, when we're thinking of the aldehyde or the ketone as a substituent, we name them slightly differently. So these molecules are just ketones and aldehydes. And the only interesting thing about these molecules is they're ketones and aldehydes. And so when ketone or aldehyde is the most interesting thing of the molecule, we do that nomenclature. But if you look at it as a substituent, I'll show you an example. So here's an aromatic ring. With an aldehyde. So what do you think the base of this molecule is going to be? What do you think the base of this molecule is going to be? It's benzoic acid. So when the base is not the fact it's a ketone or the aldehyde, like in these cases, when there's a more important base, like in this case, this is benzoic acid. Now we think of the aldehyde as a substitution. And so what we would call this would be orthoformal. So aldehydes can also be called formal groups. Well, formal groups, if you have a hydrogen, well, formal. When they're off benzene rings, you can call them formal groups, F-O-R-M-Y-L. So this would be orthoformal, F-O-R-M-Y-L, like formaldehyde, formal benzoic acid. So the only reason I'm showing you this, if I ever call something a formal group, I'm talking about aldehyde as a substituent. A formal group is an aldehyde. Finally, ketone, or let me actually draw an example. Let me do it in red. You can tell I'm really into nomenclature, can't you? So same thing, let's draw the benzoic acid. And now let's draw the ketone. So now, whereas an aldehyde we will call a formal group. This part we call an acetal group. Acetyl group, sorry. So this would be orthoacetyl. And so acetyl, we almost always abbreviate it as AC. I'll spell it out this time. But normally this thing we just call AC. Slater. Oh yeah, I'm glad some people got that. So a lot of my graduate students are too young for Saved by the Bell, so I'll make a reference like Go Bayside, and they'll look at me weird. So orthoacetyl benzoic acid. So this substitution is formal. This substitution is acetyl. Just to give an example from this last thing. So out of the nitrogen, this is still an acetyl group. So just a carbonyl with a methyl group, whether it's connected to a carbon or an heteroatom, is always going to be an acetyl group. So take home message, aldehydes end in al, ketones end in -one. If we're talking about substitution off of something like off of an amine or off of an aromatic system, then it's acetyl group, acetate, or formal group for aldehydes. Alright, now let's get to the good stuff. So let's do some quick review. How do we make aldehydes? From what we know today, how do we make aldehydes? Someone throw out a starting material and a reaction to make an aldehyde. Primary alcohol oxidation, great. And so there are a couple oxidations we can do. The key, starting from a primary alcohol, is we've got to be dry. We have to do dry oxidations. So we can do a Swern oxidation or a PCC oxidation. But those will give us aldehydes. Another way to make an aldehyde. Pretty much we haven't learned any other ways to make aldehydes, right? From 232, you should have learned ozanalysis. And ozanalysis can definitely give you aldehydes. Last semester, I taught the mechanism of ozanalysis and asked them to test, and then eventually I realized that wasn't a cool move. So, the mechanism of ozanalysis, the first step is a Diels-Alder-like mechanism. You do a cycloaddition between the O3 and your double bond. And then stuff happens, and you cleave your bond. So now if I want to ask you in like a trivia night, you can say, oh, ozanalysis is like Diels-Alder. Although I've never been to a trivia night where that question is asked. But one day, maybe at a conference. So, but nonetheless, ozanalysis can give you aldehydes. So just to show you an example. It was way too nice out this weekend. Way too nice. So the ozanalysis, you take O3. So O3 is just ozone. And you add the O3 to your double bond cold. Then this does a deal, it's not technically a Diels-Alder, but it's a cycloaddition. Diels-Alders are 4 plus 2. This is 3 plus 2. So it's a slightly different mechanism than Diels-Alder, but it's the same HOMO-LUMO interaction. Ring forms, double bond goes away, bonds form stuff. So it's cold, and O3, and then you add dimethyl sulfide. So a sulfur with 2 methyl groups. And the product you get out, in this case, would be, in ozanalysis, you cleave a double bond, and you replace one double bond with 2 carbonyls. So ozanalysis replaces one double bond with 2 carbonyls. So in this case, the 2 products we get, and we'll draw them in a different color so it pops more, is you get this fragment as a carbonyl, with the carbon in the double bond being a carbonyl carbon now. So you have your aldehyde. And then I'll draw this in blue. Then you have this fragment as a carbonyl. In this case, it's 2 hydrogens, so in this case, this will be formaldehyde. So once again, an ozanalysis using O3 followed by dimethyl sulfide will cleave a double bond to give you 2 carbonyls. Or each carbon in the alkene is now a carbonyl carbon in an aldehyde or ketone. So ozanalysis is a good way to make 2 carbonyls from a double bond. So whenever you see a double bond and O3, the product's probably going to be 2 carbonyls cleaved from that double bond. Alright, so now let's talk about ketones. How do we make ketones? And it's going to be really similar to aldehydes, right? How do we make ketones? Oxidation. Take a secondary alcohol. And this time, we can pretty much use any oxidation we want. So we can do Jones, we can do PCC, we can do Jones. I'm just going to go the generic oxygen. Did I say germs? I caught that. So you take your secondary alcohol, you take any of the oxidations we've discussed, and the product you get out will be your ketone. And we really haven't discussed any other ways to make ketones, right? The big thing is oxidation. If you try to add a Grignard or an organolithium into an ester, it's going to go twice. So you're not going to get the ketone and you're bummed out. So really, oxidations are really the only way we've talked about making ketones so far. And ozonolysis. You can use ozonolysis to make ketones as well. Here's an example that I'm thinking of right now for no reason whatsoever. I think it's on the practice test, actually. Again, you can take your carbonyl. You can take your O3, your ozone, so an ozonolysis. And then again, dimethyl sulfide. And dimethyl sulfide just quenches the oxidated things we formed. Don't worry about the mechanism, I guess. And what this will give you now is, once again, as in this case, it's going to cleave this bond and replace that one carbonyl, that one double bond with two carbonyls. And give you two ketones. So we broke this bond. Let me do this in red. We broke this bond and replaced the one double bond with two carbonyls. So we added two oxygens across that double bond and got the diketone. So pretty much we're limited to just oxidations to make ketones, right? Ketones and aldehydes right now. So chapter 16, we're going to talk about some modern methodologies and how we can use nucleophilic additions and stop just once. And we're not using LAH, and we're not using Grignards or esters. Things change, but we can make ketones from the ketones and aldehydes from the addition of strong nucleophiles into carbonyls, so carbonyl-related things. And so, and that's really what the core of chapter 6, at least the first part of chapter 16 will be. So, from chapter 12, we know that pretty much anything we take, whether it be an ester or an amide or a carboxylic acid, we know that in the presence of LAH, all of these reagents are going to give the same compound, right? In the presence of LAH, esters, carboxylic acid, and amides are going to all go to the primary alcohol via addition of two hydrogens to the carbonyl carbon. So, exam 1 step.